tell every patient with any of these mutations exactly what the underlying problem is, because it's not only excitability, like I told you, but you can have also migration disorder, so that the inhibitory neurons don't migrate right or something like this. So this all will be an approach later on to be personalized and precision. Now, as I said, gene therapy is at the moment future, and right now what we do is we control excitability with anti-epileptic drugs. And all these anti-epileptic drugs put all the epilepsy patients into one pot, even though they are not the same pot. Okay? And as a consequence, 30% of these patients become intractable. So now, can you imagine what it means? I mean, you have to just imagine what this means. Is you have a patient, you have a kid that has epilepsy. Right now, you depend on this, but in 30% of the cases, this becomes intractable. So your kid will have epilepsy through all their life. Many of these children dies, and the whole brain, basically, the more seizures you have, the more it basically starts to be damaged. So this is very devastating. And so how do we treat it right now? So if you have a patient with intractable epilepsy, they come to our clinic, and then you put these subdural electrodes on top of this, and you record from 120 areas in the brain to find out where in the brain does the seizure start. So this is now a real example of one of the patients that we had, and you can see the seizure starts in this area and then spreads out into the other areas. So you do this for 2 weeks to observe this kid, to know exactly where this starts. And then what you do is you take out this piece of the area of the brain. And just so you know how it works, this is an example from Jason Hoffman, with whom we work. So basically they identified the area where the seizure starts. And now he has to get first to this area. And it looks pretty brutal, I think. And but basically, after a while, he finds the area and dissects this to avoid as much bleeding as possible. Okay, so that's what the neurosurgeon is doing. And you can see here, this area was now removed. And in most hospitals, actually in the United States, but also in India, you do this kind of epilepsy surgery, okay? And but in most of the places, once you have done the surgery, you throw away this tissue or give it to pathology to say, you know, like, is there like a structural abnormality or not? But that's it. So what we're doing in Seattle now, and this is work done again by Rada Mirza together with Bill Dobbins and Jeff Ogerman. They start to use this tissue to do genome sequencing. So they want to know, is in this tissue, is there a mutation that can explain this intractable epilepsy? And to the big surprise is, in fact, they find mutations that are sitting in this very area that was removed, like I showed you just before. And this led to a very important concept. It's a concept of somatic mutation. So what does it mean? Now, when you think about genetic mutation, you think it's everywhere. You know, like you can measure it in the blood. Okay, so the Dravet syndrome, you can see the SN1A mutation in every cell, and you can see it in the blood. Now, in many cases, however, a mutation doesn't occur at the time of fertilization in the oocyte, but it can occur later during development. So it can occur in this very small area. You get an mTOR mutation, and now you would not see this mutation in the blood, but you see it in this tissue, and you can see there are percentage of tissues, like you see it in 9% in the focus, and in 0% in the surrounding tissue. Now, this is another example. Okay, so here, this was the focus. 9% of the neurons here had the mutation, and in the surrounding tissue it's much less. In fact, this was a very interesting part of the study because they took out this part of the patient, and then the patient got seizures again, and then they did another resection, and then they realized, oh, there was also tissue here with mutation. So what does it help us now? What they found is that many of these mutations that they had was related to the so-called mTOR pathway. So AKT to mTOR. So when you study about these signaling pathways, that's when it becomes very important, because this mTOR pathway plays a big role in migration, cell migration, etc. And interestingly, this mTOR pathway was well known to Bill Dobbins and Rader, because a lot of children have something called megalencephaly, where they have migration disorder, so that the brain grows too big. Now, this megalencephaly is actually very, very rare, but because it has to be the germline to be megalencephaly. But what they found is that basically the same mutation that happens in the germline can now be part of the somatic mutation, and can lead to a small kind of megalencephaly in this cortex that then leads to the seizure. So now suddenly something that is very rare becomes something very frequent, because focal cortical dysplasia is very, very frequent. But of course you have many different degrees of megalencephaly now. So some bigger, some smaller, etc. But they have a whole spectrum now of these brain malformations in these children. And they are very well known. Okay, so these PIK3CA and mTOR pathway mutation, they lead to overgrowth because they're migration disorders. Okay, so you have big legs, you have a big cheek here on one side, a big side, and you have also in the brain these megalencephalic growth. And having the understanding of the mutilation now allows us to target the different parts of this pathway. So you see this recurrent theme. By understanding the mechanism, you have a therapy, because now you can see, what kind of drugs are out there that target these different areas of the brain, okay, of the pathway. And then you can use these drugs that exist, like rapamycin, in order to start thinking, can this help my epilepsy? And there are early signs of success. So this is not from our lab, but this is another study, I think it was in Nature, where they targeted the PIK3CA overgrowth. And indeed, when they did this, one second. Anyway, I don't have it, I forgot to put this slide in. They were improving the anatomy of these children. So what we were surprised is to find so many disorders of epilepsy related to the mTOR pathway. And we think the reason for this is that humans underwent a dramatic, explosive evolution. So when you see the growth of the brain, then you can see only the last few thousand years, the growth of the brain basically exploded. And when we look at the mouse, there is this intermediate zone, the subarticular zone, here, where all the neurons are born. Now in the human, this area is huge. It actually developed, so basically, because the human brain has to develop so fast, so strong, it has a lot of migration issues, and if you have a mutation here, then you get epilepsy. Okay? So basically, we're thinking that the reason we have a lot of those migration disorders, focal cortical dysplasia, and 30% of the intractable epilepsy is it's a typical human problem because of our size of the brain. And so how do we go from there now? So how can we develop therapies? And one way to do it is actually something called the Ipsc approach. And I told you this already when I talked about autism. Because what we can do is we can take a hair cell, again, from a patient and turn it into nerve cells. Now in this case, what we can do is we can take the tissue that we have excised and turn it into nerve cells, and then grow these, we call it the organoids. Or we can do the following: we can take the hair cell and then insert genetically the mutation that we have analyzed in the seizure focus. And we can titrate this. We can put 10% of these cells into this mutation to mimic exactly the seizure focus. And then we grow these organoids, and you can see that the more we put of this mTOR mutation, the bigger the organoid will be. And now we can actually stick electrodes here and see at what point do you get seizures, and that allows us now to not only treat the seizure but also understand the seizures. So the key part where we are now very much involved is understanding how does this migration lead to hyperexcitability in epilepsy. And you can see this pathway is hugely complex. And we have to understand, how does it change the membrane in order to cause excitability changes. And we think this has something to do with the phospholipid membrane. And so we're making, again, mouse model where we mutate it and do electrophysiology. And this is shown here. So here, again, collaboration with Frank and Kathy Millen. So we have a mutation identified in a human. Then we make a mouse, and you can see the mouse has a bigger brain or bigger size than the control. And the mouse has also seizures. And then we can apply very specific drug, and indeed within 45 minutes after applying the drug, we have a seizure medication. So again, you have to realize how important this is. I told you 30% of the people with epilepsy, and these are millions and millions of people, are not treatable. So now we have a new way to treat these patients. And of course, at the moment, we do it only in mice, but we just started now a clinical trial with rapamycin, but we're now trying to have also other drugs that hopefully become available in order to treat then very specifically these patients. Okay, so this is the clinical trial. How am I doing with time? I have no idea. 45, okay. So there's a whole other story, okay? Oh. So I focus on the genetic mutations, okay? And the genetic mutations, of course, is not everything, as I told you. And another reason to get epilepsy is actually traumatic brain injury. So 30% of patients with severe TBI will develop epilepsy. So I can imagine that, let's say in India, when I see the people with the motorcycles, I think you will have a lot of people that will develop epilepsies that are not genetic, but they're really caused by the traumatic brain injury. In America, which is a very aggressive country, we have a lot of people because of the military. So they come back from Afghanistan, Iraq, and many of them develop epilepsy. And so this also now triggers another research area, which is not a genetic research area, but we want to understand how does inflammation during a seizure lead to epilepsy. And the problem here is that you have a traumatic brain injury, and within seconds you get a cytokine storm, you get reactive oxygen species, but then days afterwards, you get changes in neurogenesis, changes in apoptosis, cell death, etc. And then weeks and years later, you will get an hyperexcitable cortex. And we call this the silent period. And we have no clue exactly how this TBI leads to seizures and how we can change this. And so a lot of research we put in this right now to understand, how does inflammation lead to network remodeling that then leads to excitability changes. And again, we use the same approach. So you have a cortex that has a seizure focus. And again, what we do, instead of throwing this tissue away, we can take this tissue. Okay, so I want to show you what we do. So this is after the operation. This is the tissue we get. And then we have to first make sense of the tissue. We have to say, you know, what is the apical layer, what's where's the gray matter, where's the white matter, and then we orient it and put this on a block, an agar block. So you see we put the tissue on an agar block, oriented it, and then what we do next is we start to cut it. So we put it in a vibratome, and then we cut it in slices. So happens everything immediately after an operation. So normally these operations, they take like several hours. So by 5 o'clock in the evening, we start to get it. So this was 4 o'clock in the evening. And then we start to cut the tissue, see in 100 micrometer thick slices or 300 micrometer thick slices. The tissue is still alive, so we have oxygen in there, etc. And then once we sliced it, we put it into these baths. So now you see it's 2 o'clock in the night on Christmas Eve. My wife was not so happy. No, I was not so happy. Sorry, my wife knows me. And then basically, once you have this tissue, we do electrophysiology. So basically, we start to put these in the bath and then stick electrodes in to ask the question, why are these neurons hyperactive? You know, what could be the cause of epilepsy? And we do this now, you know, for many, many years. When we get the tissue, all it takes is give the, you know, like my people some pizza, and then they work forever. You don't have pizza here, but I'm sure you have other ways to make them excited. And then we record from cells, and you can see we get these hyperactive cells, and that gives us an idea, you know, what is the mechanism and what is not. So I don't know how much time I have, but basically we go and characterize the electrophysiology of these cells. We find differences between the focus and the non-focus. We identify, you know, intrinsic mechanisms. We identify synaptic mechanisms. And I go now very fast, but basically we find that in the focus tissue we get much more of these large depolarizations compared to control. So these are so-called paroxysmal depolarization, where you get a sodium channel block, and then we count how many do we have in the focal versus non, and then you see there's a statistical difference. So then we ask the question, why is this more excited than here? And interestingly, what we find is that only in tissues in the cortex where there was no pathological abnormality, we found a major difference. Whereas in the patients where they had migration abnormalities, there was no difference. And this was kind of interesting for us, because right now what we're thinking is that these tissues are due to the mTOR pathway and due to the genetic mutation, whereas these tissues are probably due to a traumatic brain injury that caused a homeostatic change in excitability. So that now allows us to devise different ways to understand the epilepsies of these different patients. So I want to go on. So we have some ideas. You know what, I want to go just to the last slide. But you know what, I lost everything here. Come on.
It's coming back. Yeah, there's this.
I want to end a little bit with the concept, you know. So basically, we divide the cortex now in those where inflammatory pathways have led to the seizure, and those where somatic mutation led to the seizures. We try to develop therapies for those patients, like rapamycin or other drugs that act on this pathway. Here we try inflammatory pathway drugs in order to treat these. But I think the principle that you saw, this this understanding the mechanism that underlies, in this case, epilepsy, will help us to develop personalized medicine for these people. And of course, what I showed you was just one example on epilepsy, but you can think about this in the same way for autism. So these are all mutations in autism that are all centered around the glutamatergic synapse. But again, understanding one mutation doesn't help you. You have to understand how all these interact and devise also then very personalized therapies for autism. And this is kind of the approach that we want to take for all neurological disorders, instead of saying, okay, you have autism, you get this drug, you have epilepsy, you get this drug. We want to really get into the mechanism, and for this, you need a team. And this was our center in 2009 when they recruited me, and now we're full, so we're like full house. And this was 2012, and I think I wouldn't say we doubled, but we now have 2 floors. And the key in all this endeavor, in fact, are not the old guys here, these Ninos and the Erics, etc., and Bills, but it's the young guys. So it's you, okay? Because what we find is that it's the young people that know all these new developments. Like you learn about this signaling pathway, you learn about genetic techniques, you learn about CRISPR. When I was young, at your age, I had no clue what CRISPR is. I had no clue. I was a neuroscientist. I didn't know about genetics. But you guys get the training in this, and then you are starting to work with all the other colleagues of yours that have professors that specialize in neuroscience, that specialize in genetics, and then you combine these techniques to develop new concepts. So I think the future sits in you, where you have to bring the knowledge that you're learning now into the future by actually transforming medicine. Because right now, I tell you, neurology is a pretty depressing field, because, as I said, you have an epileptic patient that you cannot help, or an autistic kid that you cannot help, and there's nothing more devastating. So that's why I think you better learn, and also see how you can apply your knowledge to the future. So that's what I wanted to tell you. Thanks. You see, there are some people. We have several people from India here. Like here, I have Shilpa. Where's Shilpa? Shilpa here. And hey, Gustavo, thanks for your attention.
Yeah.
No, sorry.
Fascinating talk.
Okay, good. This is Bolivia. This is going on in Bolivia. Okay.
I think the students, if you have any questions, you can please ask Professor Ramire.
Yes. Yeah, I hope you don't develop epilepsy just by listening. Your hyper-excitable cortex.
Okay. Can I have the question when
Dr. Das, yes. You're the future too. So.
Oh, yes. I just like to ask the question because in your process you have mentioned that one of the way that is the IPSC.
Oh yes.
Yes, that's the one of the prospering and the hope of that for treating the epileptic patients.
Absolutely.
But my question is that when the personalized medicine, when you select an or basically based on the gene, and when IPSC, most of the times it needs at least one oncogene for developing the IPSC.
Yeah.
Does it try to cure? Can it develop certain type of tumors?
Yeah. I tell you, I'm so surprised. I'm really surprised because I was skeptical. I'm so surprised how similar, in fact, these organoids reflect the disease. So, for example, radar is getting the hair from megacephalic patients, and these organoids, after 1 year, are bigger, twice the size of one without megalencephaly. Then she takes patients' hair from microcephalic patients that have a too small brain, and that brain, these organoids are smaller, and they develop seizures. And then basically, once you have these organoids that are bigger, you can ask the question, why is this bigger? You know, which cells are growing? And then you find that basically it's these proliferative cells that we have also in the cortex. So you get much more specific insights into this. And on top of course, asking the question of why do they start to seize. But I think what your point is well taken, and I think it's a very important point. And I think that's also the reason why it takes a team. You know, because if you only do iPS cells, it's not enough.
Yes.
You know, you have to have also a human geneticist that brings you into the mouse genetics, so you have a mouse model. And then you have a mouse model, it's also not enough. You know, you have to have a molecular biologist that can ask the question, you know, what is in this pathway really effective? You need someone who just does proteomics. And I think that the power of these institutes, you know, the power of this institute is that science is moving away from one lab to team efforts. You know, so when we publish something, we have 20 authors, because you have the human geneticist on it, you have the mouse geneticist on, and every part is important. So that's why we call ourselves the Center for Integrative Brain Research, because it's not enough to have one lab anymore. And I tell you, visiting here, I think it would be very good to have an institute, you know, because, you know, most of the research that is combined here is normally done in different teaching departments. You know, the geneticist teaches in the genetics department, the anatomist in the anatomy department, the physiologist in the physiology department. So what we have done is bring them all together. And by bringing people together with different backgrounds, I tell you, I was scared, okay? Because what could be is that the human geneticist never talks to physiologists, so you create a little islands, you know? But why this didn't work, why it worked, was because of you guys, because of the young generation. Because the young generation, they go out to the bar in the evenings, on Fridays. And you know, and they're nerds. When they get a beer, they talk science. You know, they don't talk about whatever, politics. They talk science. And then they go on Fridays and Saturdays, they go into the lab and they test something. And so it was the young guys that did a lot of the collaborations, and they learn each other, you know? And so I think thinking team science is important, because every single approach has a flaw. But together, they give you insights. Yeah. Good. Gustavo.
Let me get the speaker. So I want to comment that what you have seen here is really amazing. And let me tell you why. Because you are studying traditional medical education, okay? And that's fine, and I've been through that many years back in Bolivia. But it is such a changing and dynamic movement going on now that what you have seen can change completely the focus of how medical education should go on from now on. And I think it's a wonderful, wonderful privilege to have Nino here show you this. This is really, he's the leader of all this, and he is the leader of the second most important, significant neuroscience center in the United States. That's not easy to achieve. And let me tell you, and it's true, and I think Professor Kusal Das has brought you a jewel here that not many medical schools get the chance to see, okay? So, but let me tell you also that what he's showing you is leading edge technologies. I do have a question for him, but I want you, because I was also young, and sometimes we don't realize what we are seeing. As we get older, we are able to really capture the true value of what we have seen. So what you have seen now, go home, meditate about it. It's going to be online, I understand. You have to go and see this video 5 times. I'm not kidding you. You have to read it because